myself. Yes, I made myself. All right, share screen. So as I promised, we are going to play with the software. I posted the link in today's module. And yes, I was not creative, did not create the obstacle myself. I just copied theirs, but it's cool. So we're gonna see how it works. Let me take all of this off. This was your assignment, right? So you had to first identify all these vertices. Sorry, my apology to I think you, because you thought that these corners were part of it. I think that's, but it's fine. So yours answer is slightly different, but it's okay. So the polygon points are these points, but this was the environment. I changed the figure. I don't know if you saw or not, but it's okay. So from here, from the top left, like not top, from the left side, and then you kind of sweep. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until 13. So we sweep and find all the edges. Then if I'm right, to show vertices, so you draw lines, upper and lower. So all the uppers are, well, their uppers are in red. You didn't have to do that, just to understand better. So you see that 0 of this doesn't have any lines, so some of them won't have, like our example, the number 5. That was there. So this one, the lower is blue, upper is red. Q doesn't have upper, so it just has lower. So lower to the next obstacle. So wherever you reach to the obstacle, you stop. So this was the point of draw. This is the point of draw. This way cannot go. So you see that this is now divided in different sections. So we draw all the edges. Now we're going to show our trapezoids. So all of those are marked now. 0, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8 until 14. And then gonna draw all the vertices. So this is supposed to show the graph here. It doesn't show. Refresh trying. Well, no, it doesn't show. Map 2, map 1. I don't know, it doesn't show. So this is supposed to show all of these vertices. So from 0, 1, 2, and then connected wherever there's a common line, you connect those two together. Now this software, well, it's a software that they wrote. Pretty cool because you can, oh, there you go. I had to change it. So you can change the edges if you're interested to see what happens. If you go click on the edge, you'll see that your graph here will change. Now you can find the shortest path. There's another map loaded. If I think I changed something here, you can see that. So that's a more complicated version. So if you have question how things work, what if some of them were in some other point, you can check. We cannot connect them to the edges. We are assuming there is a distance between them. They're not overlapping. So play with this. I'm gonna post a solution for class participation, but this is a good way of step-by-step see how it changes. Yes. What was that question? The purpose? The vertices start with 0. Oh, here you mean this one or this one? Both of them. So let me take this off. So these are 0, 1, 2 are these 1, 0, 1, 2 that you created. But then when you see the vertices is basically, if you were going to move, you are going to check. You remember that I said A star algorithm is going to use the halfway point. So that is for if you are going to implement an algorithm, you have different ways. You could say that I'm going to go from the middle of this area, measure my line and go. If you go that route, in some cases, you might actually, if you go from 9 to, let's say 11, if you go from the middle of this area to middle of this, you have to cross your obstacle, right? That's why if you make it the middle of that edge, then here connect to here, you ensure that you do not cross the obstacle. Make sense? Because the lines are only when there is free space. So you could have different methods, but this ensures that you never cross an obstacle, because in an algorithm, you're going to tell your robot, the robot does not have any other information. So this is just to show, if I pick a path, you can connect them. So does that make sense?
Yeah. It is using a mixture based on which one.
So the problem here is the shortest path. So right now you don't have the weight of these, like the distance between them. Once you have this, which today we will see, all of those edges that will have a weight. Then we will add them together and see what is the shortest path. So for the class participation, I asked like estimate the shortest path to just kind of visually like, okay, if you go from, I don't know, my goal from 0 to 4, 11, 12, 13 probably is the shortest, because we don't have numbers here, right? It's kind of you're estimating. But in the actual problem, you will have weights for every edge. So you actually add them together. It wouldn't be in the middle, it would be the weight of that, the distance of that. So think about nodes and distance between nodes. So weights can be a mixture of the distance, how fast you can get, how easy access it is, depending on the problem, right? Then we come up with a weight factor, and then we will add them and find the shortest path. So for this here, if I take these vertices out, this would have been the class participation. From here, you go do that, connect them wherever they're a common edge, and then you'll say that, okay, by observation, this looks like the shortest path for now. All right, so this is that example. I'm going to take this off, annoying me and you probably. Stay here since I'm going to be in here. I'm going to use this PowerPoint today. Share screen, see if it works if I do that. Hopefully it works for Zoom. Finger crossed, I don't know. Okay, so today and Friday, we will discuss path planning methods algorithm. Your homework is already out. It's based on the information from yesterday, today, and Friday. Some of you already know these. So interject if I said something wrong, or if you have like better example. So for Friday, I will ask you to go and find application examples of these algorithms in your field of study. How do I get rid of this? Floating, yes. Okay, so path planning is basically finding a collision-free path between your home or start state to your goal state, right, with a minimum cost. Sometimes you're looking for shortest path, sometimes you're looking for fastest path. Time is going to be, so that cost function, that cost estimation really depends on what the project is. So you have to identify that. Then we will minimize that. So the algorithm will try to find a minimized value for that. Now we have two different strategies. One is uninformed search. The other one is informed search. Very easy to remember. So uninformed search does not use any information, right? So it's what kind of brute force? Just checks everything, searches everything until it finds the solution. Like me and John were talking, let's say you're in that map, you're looking for a blue tag. You don't know where it is. Well, you have to search the whole building to find the blue tag. But then once you find it, you now know it, right? That this is the direction to the blue patch, the blue patch or tag. So those algorithms, I'm going to, like the two examples, very familiar, famous, breadth first search and depth first search. We are going to talk about the breadth first. So the red ones are things that we will talk about. The other one is informed search, uses some kind of evaluation function. So you have to add some knowledge to your algorithm. So it's not brute force, smarter, slightly smarter. Is a greedy search or Dijkstra algorithm and A star. So A star is an extension of Dijkstra. It just has an extra function into it. So kind of smarter How does this work now? Yeah, there you go. So breadth first search or BFS or traversal search, you might have heard it. The algorithm basically wants to visit every vertex and edge exactly one time. So is that the traveling salesman problem also? No, it's not. So you cannot go back to a vertex. Just can do it only one time. What's that? Okay, Euclidean, that's for a star. Or maybe there is, I don't know, yeah. I don't know, but I know it as BFS. So the order of visit is important because you cannot go back to the previous one, right? And it depends on the problem you're solving. And also, you have to keep track of the vertices that you visited, right? So when we say that, think about, for today, whatever we discussed, think about algorithm. So when you're saying that it is important to track which vertices have been visited, so we're gonna probably have a Q vector and have a visited vector, right? Something that we can put things from, okay, have not been visited, then have been visited. So the algorithm basically works on like two buckets. There's a bucket of I haven't done anything to them, and a bucket of I've done, I'm not gonna touch that again or go visit that again. So this is for the first one that we cannot visit again. You see that here there is like, so we can call it nodes, we can call it vertices, it doesn't matter, different terminology, just make sure you're using the same terminology. When you're reading literature, you'll see both of them, but they will use probably sometime mix and match the terminology. For this search strategy, your graphs can contain cycles, which can bring you back to the same point while traversing the graph. We can usually use Boolean to avoid visiting the same node. So it means that once you visit a node, you can turn the Boolean on. So you know that has been searched. So your algorithm does not go back. So you can check if a Boolean is 1, don't go check. Or Boolean off. So you can turn on, have a state on and off if you're working a state machine. And while visiting the nodes, you want to make sure that you have the same strategy for visiting the child. So parent is the top node, child is the bottom. So have the same strategy to check them, right? And to make it easy, we're going to have a queue, which I talked about, and a visited vector, so we can keep track of everything. So we do this through an example. Let's say that we have 6 nodes. That's how they are connected, right? So wherever we start our home state, there's always a start state. Here we're going to call it source node, right? And we're going to have a goal, but here we're going to visit all of them, right? Once. So we start from one place and then going to visit all of them, make sure they visit all of them. So creating 2 vectors here, let's say I'm going to call them vector, but I can call the bucket. So one is our visited. So 1, 2, 3, 4, 5, the nodes, there's a queue. And you can have another one that is printed or visited, right? So you can have kind of 3 things, all the nodes, how we're going to queue them. And then once we visited, you could put it in the visited bucket and you'll see that it's called printed here. So it's kind of a piece of code. You can use, most of the code I use, I grab from internet as well. And they're mostly either in C or Python, C++ or Python. So you see them. So we're kind of shifting from MATLAB. And you still can do these in MATLAB as well, but usually these are more in Python and C++. Okay, so starting from here, the left side, we are at our source node, node 1. You see that in visited, we can put 1 Boolean, right? So all of them were 0, not visited. Now the first one is visited. We are at number 1. So we can change the 0 to 1. And then now we put 1 in queue. We haven't done anything. We just started. The next step is, okay, visited 1, you're printing it. So out from the queue line to print it. Now, what is 1 connected to? We have to move now, right? So if that was our parent node, we're going to the child. We're going down. What is connected to it? 2 and 3 are connected. So we are going to the step 3. You'll see that there is 1, 1, 1 now. So 1 and 1, the booleans are on for 2 and 3 because now we are advancing or acknowledging these two are connected. We put 2 and 3 in the queue, right? We don't print them right away because we don't know which way we are moving. So now we decide that, okay, let's go to 2, right? So if you're going to 2, now 2 becomes printed and we are seeing that, so 2 is connected to 4 and 5. So now 4 and 5 going to be visited. So I'm going to turn the Boolean on, put 4 and 5 in my queue line. So these are the next ones that I'm going to go to, right? So 2 have been already passed through. The next ones are 3, 4, and 5. Remember that it is important, the sequence of visit. Now, picking up from here, let's say that we did 1, 2, 4, 5, right? We haven't visited 3. 3 was in the queue. Now we visited 3, and 3 is connected to 5. So 5 gets the Boolean on. Yes.
How have we visited 3? Well, so there's the requirement that we can't pass through the same node. Like,
So you are going down. It's not that you're actually moving and then you have to go back to 3. So you see that here they were connected, right? You could go to 2 or you could go to 3.
Yeah.
If you would go to 2, you would be connected to 4 and 5.
Yeah.
If you go to 3, 3 will connect to 5. That's the order that we will put here.
But if the last thing we visited was,
We haven't visited 4 and 5 yet.
Well, so if we're at 2,
Yeah.
2 is not connected to 3.
Yeah.
How do we visit 3 without passing through 1 again?
So no, we didn't pass through 1. So here is like from 1, we are doing parent to child, remember? So if 1 is parent, it is top layer, the next layer is 2 and 3. So we go into next layer, we say, let's visit 2, that would take us to 4 and 5. We're not gonna go down to 4 and 5. We're gonna check what would happen if we go to 3. So we are going to same layer, finish the layer and go down. So at the end, we will find what is the shortest path. We will basically, we will also record all the weights, how much it would take you go from 1 to 2, 2 to 4, 2, and then 2 to 5. We will record those in our algorithm if we decide at the end to go find the shortest path. Right now, we're just doing the search, making sure that we are going through all the nodes, recording all the weights, right? So that's why if you notice here, we had layers, right? So layer 0 is our parents, layer 1 is the child. So we're gonna make sure we go all of this. Then we go to layer 2, make sure we check everything in layer 2. Then we go to the bottom layer while recording all the weights, and then we can find what's the shortest path, right? So that's why this is brute force. You're not actually deciding which way you're going. You're just checking everything. Once you have the information, because these are uninformed, right? Once you have the information, you say, you know what, now if I add these, I'm gonna have the shortest path. So you're gonna have to do it again. So basically think of it collecting information phase. So here, 2 was visited in this layer. 2 is connected to 4 and 5. You just put it in the queue. Now, there is 3 still in that layer. We're gonna say, okay, if we put visit 3, right? 3 is connected to 5. 5 is already in queue. So we don't have to add anything else. So we're gonna say that, okay, we visited 3. 3 was in that layer. Now, next layer is 4 and 5, right? 4 and 5, which one do you want to go first? 4, we're gonna keep an order, right? We'll follow an order. Let's say 4. We're gonna say that, all right, I'm gonna visit 4. 4 is in the queue, goes here, and then now 4 is connected to 6, right? So you can say that 4 is connected to 6, so 6 can be added to your queue, but you still have to go to 5 first in the same layer. Find how much is the distance basically from 5 to 6. So you're saving the distance from 4 to 6 and from 5 to 6. So collecting this information. Now I'm at the end of my search. I have visited everything. I have recorded all the information, how the nodes are connected. Then once you have those, you can decide that, okay, maybe 1, 3, 4, 5, 6 was the shortest path, or 1, 2, 5, 6 was the shortest path. You will add all of those values together. All right. So in an uninformed search, you're going to search first. Let's get to know my environment. Okay, there is a system. So this is basically the system of your search. After this, now let's decide what is the problem. Is it the shortest path, the fastest? I don't know. Depend on what the objective of the project is. And then the time complexity is V plus E, which V is the number of nodes and E is the number of edges, things that you have to go through. So you have to visit all the nodes and you have to go through all the edges. So that's how you add the complexity for this. This is a pseudocode. If you want to write the code, basically, it's the same thing that we just went over. Having a queue, moving from queue to visited, and then to print or done. Now, the next algorithm is informed algorithm. We start from Dijkstra and then we go to A star. So you see that, as an example, you started from a corner point here. This is an obstacle and it's searching. You see that it's searching everything, right? As it goes, is expanding and trying to figure out all the distances and then still searching. This hasn't decided where to go. And you see that it is getting closer, still looking for everything until it gets to the goal, then draw the path. So this algorithm collects more information as needed, right? Again, it's just searching through all and doesn't care if the distances are shorter or farther. It's collecting information. At the end, once the search reached the goal, then it will go back and find, okay, what was the shortest path? So for your homework, you create that table, find the search, you do the search, then you can find the shortest path, right? When you have all the information. So starting from an initial vertex, and then the path starts until you get to the final. And the idea is you start from a vertex and then you're connected to different one. Which way you start the search? You start the search where there is lower cost, lower distance, lower weight. Then once you're done with that, since you have to visit all the vertices to see what are the other scenarios, you have to go back and find all those as well. But the idea is to use the shortest path instead of brute force, just find everything. Let's just go with the shortest path. And you will have to check all the neighbors of a vertex. So you can't just leave one alone. And once you reach, then we can find the shortest path after that. Now, here I'm going to explain the search pattern, the search algorithm. For your assignment, for your homework question 1, after you've done this, then you will have to find the shortest path. Which one would be? Now you have all the gains, all the weights, then you'll find. Let's say that we have some nodes. This is a very popular example. If you search Dijkstra example, something like this will show up, maybe different weights, but kind of having everything. So a couple of things we have to do. We have to initialize. So you have a source node or the node that you start, right? The initial node. That node gets a weight of 0. Here, let's say we start from A. Every other node will get a weight of infinity. Means that the cost to get them is infinity. Just giving a very large number, we're going to update this as we go and then find an actual value for them. Then we can find the shortest path. We will create a queue. Again, we are working with this algorithm. We need to have unvisited queue and then a visited vector. So our unvisited queue, or whatever you want to call it, which includes all the nodes, with the gains that as we update these nodes, these gains. So 0 from A, and everything else is infinity. And this is a list of our visited nodes. Does not mean the sequence will show you the shortest path. Just means that this is how you visited these. All right. Now to start, we're going to start from A. So from A to go to B will cost you 10. To go to C will cost you 3, right? Now, how 10 and 3 were measured, this is depend on the project, depend on many factors, not just distance. It could be time, it could be, depend on really what, because these have application in networking, in computers, like routing. If you have like in telephone network, where is the closest station, to get to? So have different applications. Now, depending on that, you will find these weights first. So you set up your problem, then try to solve it. Now, so we will update those infinities to actual values to go from A to B and C. In our table, you'll see that the infinity value for B now is 10, C is 3. We already visited A, we are going to move to one of these two, right? We are gonna put A in our visited. Now, the idea is that Dijkstra uses the shortest path. It doesn't care about layers of parent-child. Now, this is more of what you would think. Which way it will go? Shortest path? C, right? It's only costs you 3. So next we will visit 3. We will visit C. It costs us 3. So C, we are visiting it. It will go to the visited vector. Now we can access to B, D, and E. It will cost us 2 to go to E. It costs us, so we are going from our initial point, right? So 3 plus 8 will be 11. To go to D, and don't forget, the goal here is to go from the initial point. From A to D through C is going to be 11, right? And through here is going to be 12. Through here is another point. So you see that there are different ways of getting somewhere. So now finding the shortest path makes more sense. Now, let's say that we can go all 3 of them. From C, we can go to D, pay 8. We already paid 3, so that's 11. We are going to change that infinity to 11. Then to go to B, it can cost you 4. So 3 plus 4 is 7. So previously you cost 10 if you go directly, right? Now, if you go through this one, it's going to be lower cost. So now you see that the layer doesn't make sense anymore. You don't have to go to B from A. So now this way, this is one way to get to B and cheaper. We're going to update that weight. Now, putting C in here, now we're going to decide which one to visit next. So based on the algorithm, which way we're going to go? Ben? E. Why? Because this has the lowest cost, right? So the algorithm runs based on what's the lowest cost to go to the next neighbor, right? So you're going to E, and then the cost of going E is 3 plus 2 is 5. And then now you have to decide where to go because you still have 2 more vertices that are not visited, right? You have to visit those. Now, if we go from E to D, it's going to cost us 5 plus 9. 14, which is more than 11, right? So this is probably not the best path to go from here. So the value for D and B will stay the same as the lowest previously. We're not going to update it. You're not going to update D because it's going to cost us 14, which is more than that. And then if you go from here to here is 5 plus 9 plus, you cannot go here. So this through E, you cannot get to B, right? So, but we already visited, we already gained the information. So we're going to put that in our visited. Now you'll say that, okay, if I go from C to B or to D, if I go from C to B, 3 plus 4 is 7, right? Now from B to D is going to cost me 2. 7 plus 2 is 9, right? So lower cost. So we can update the cost of going to D to 9 through C. So AC to B to here would have lower cost. Again, we're just doing the search right now because you're saying that, okay, if I go here, 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 how am I going to go back? But you see that there is a turnaround here, 1, that you can go back and reach again there, right? So we visited all of them. We haven't visited D. We are going to go from B, cost of 2 to D, 9. Now everything has been visited, right? From the algorithm. So the search is done. Now remains the shortest path that the algorithm has to find. What's the shortest path now to get from this information from initial point to any of these. We don't know where right now, we don't know where our goal is, right? So the goal could have been B. What would be the shortest path from A going to B? ACB, right? So now when you decide which one is your goal node, then you can find the shortest path. We have done, the search is done. Now the next question, where you want to go? I have all the information, I can find it for you. So for your assignment, I think I didn't give you the goal, right? I don't think I did. Just do the search. Yeah, I think I didn't, because you already submitted. Does this make sense? What happened here?
So in this algorithm, you would ignore the path altogether. You wouldn't even like consider it and say, oh no, this one's lower, you wouldn't even take that path.
Yeah, because it doesn't work for you, because you already found the shortest path already in it. So because this is not a brute force method, you don't have to visit everything. So in BFS, which is our uninformed, and you didn't have any, so here you have a condition, you have to go through the shortest path, right? So you don't have to visit everything. So previously, the complexity was E plus V, all the vertices and all the edges. Here, lower complexity, because you don't have to actually visit everything, right? So the search, through the search, you're finding what are the shortest paths between the nodes. Now, if someone asks me to go to D, what's the path from A to D? The shortest path? ACBD now. You already know, you didn't even need to consider 8, right?
Yeah, but what happens is like 2 and 2, like 15, right?
Well, that your search will be different. This will look differently.
But you would still hit C.
So if 2 was 15, if 2 was 15, you would not go to CBD. You go A, C. So 3 plus 8 is 11. And the other way, ACED would have been 14, so it's still not a good path. So you would choose ACD. So you update it here, ACD. So the cost will be 11.
But when you're at C, you only see the one with big, right? So it would compare 4 and 8 in order to like go to the next node. I would say, all right, let's go to B.
Adjacent to C,
evaluate that higher, and then you have to go back to C.
there are 3 nodes that are adjacent to C, right? B, D, and E. Your algorithm checks the distance between all of them, no matter what is the weight. So if you're changing the weight, that will impact the search result, right? So basically, the algorithm is eliminating the longest path, so less computation. It will find you a path to connect these. That is the shortest. There might be different ways of going. You see that there are loops there, right? So you can go from A to C, B, C, E. That might be shorter, right? So depending on the search will you find that information, but the search doesn't do the shortest path. You still have to say, now minimize this to get me the shortest path. The question will be, where is your goal node? Where am I going? Because right now you don't know where you're going. You're just trying to find all the shortest way to get to some nodes. And then once you have that information, then you might actually do that A, C, going back to C, D, E, B. I really don't know if you change the weights, how it's going to play. You have to do all over again. So some of these that are empty might be full, and then the 11 over 9 might not even look like that anymore. So when I see, like when I work with algorithm, or like I don't do as much, but when I do, I think of it as a puzzle. I'm solving a puzzle. That's my or playing a game. Everybody has different ways of solving puzzles, right? So when you're writing this code, you can make it slightly better and perform a few more seconds faster than someone else, and your algorithm is better. So Dijkstra is the search algorithm you can use, and is based on shortest path. Now, if we wanted to make this better, more efficient, they came up with A-star algorithm. They say, you know what? Keep this shortest path, also have an estimation how far I have until my goal distance. Now let's only find the path that are within that distance, for example. They're using Euclidean functions. So first of all, this is a pseudocode of Dijkstra, algorithm, same as before. It's basically the same thing that we saw. You can find the codes for all of these algorithms online. That's why it's not part of your program assignment or anything. And everyone uses them, so it's game for everyone. If you're interested, So your assignments were play with some code online, but you can see the back code, what the back code is. You can write those and have your own website and does all these search. It's nothing extraordinary. So A-star algorithm is basically using a heuristic function. Says, okay, you have the shortest distance. Let's add some other functions to make this search faster. So you see that it goes to the obstacle, and then it just goes by the obstacle, finds the shortest path. Why it did that? That part was that Euclidean distance function, for example, because that, oh, from here to there could be a straight line. I'm gonna try that, see if I can get. So it eliminated all the other search, right? So you could add, so that's the part that you could have your signature in the algorithm. I'm gonna use this function because of this, my problem. This gonna probably be faster. So coming up with that function and make your search faster. If you, I don't know, thousandth of a second can make or break a project or be $1 million cheaper, expensive for your project. All these gaming company, Facebook, I don't know, Google, all they do is try to make a code slightly better, right? The algorithm basically. Make it faster, they make more money, right? And you can see the difference between both of their performances. See how fast that one is, because it knows the object is gonna be, the shortest path is x squared plus y squared, right? So it knows it has to go that way. It sees the obstacle, so it knows it has to go around it, and then it reaches the obstacle. The other one is not around the obstacle. So it sees the goal, sorry, the other one is not around the obstacle. Now, depending on your problem, maybe you want to use this, and a lot of problems have been solved with Dijkstra, you know? Then before that, you have that BFS, the brute force one, right? That just checks everything. And it's like, okay, once I check everything, I'm going to tell you what the shortest path is. Really depend on your application, you could choose any of them. These are the three famous, easy to find their code and examples. I'm going to find a few good examples for a Friday class, so we can actually see some algorithm like in robotic working using these. Some more exciting. I think the other thing I want to touch base on is RRT. I think with that, you will have some at least vocabulary or knowledge basic about algorithm of path planning. And then if you wanted to continue, you can decide just working on project. MATLAB is full of projects solved using all this algorithm. Which I'm gonna use one of those for RRT example. For Friday, I'm gonna probably have in class quiz or something. I'm gonna make sure everyone is here. I wanna kind of wrap up on Friday. Monday, if there was something left from Friday, I'm gonna finish. I'm planning not to have class on Wednesday, so you all can take a break and study. But make sure you're here on Friday and see what will happen, and then we decide for our next week. But the goal is not to come here on Wednesday. All right, sounds good? Don't forget your homework is due next Wednesday. Yeah. All right, SCIs are out. Don't forget, I'm going to remind you, but I'm not going to send announcements. All right. Stop sharing.